Hello friends, welcome you all in the physiology lecture, and today we are going to discuss about the one of the most important and fundamental topic in the physiology, that is RMP, resting membrane potential. This topic is not only used for the university examination but also it is a very important for the NEET, PG and next preparations. And also the concept of the RMP, it is used in the multiple places in the physiology. So we go. So this belongs to the competency number 1.8, that is the general physiology. Describe and discuss the molecular basis of the resting membrane potentials and action potential in excitable tissue. So here today we will discuss the RMP, and in the next session we will discuss the action potential. How we go? So start with the definition of the RMP. After that we will discuss the normal value. Then recording of the RMP, how it is recorded. Then genesis of the RMP, this is one of the most important topic. In many times it is a frequently asked question as a short note or short answer question in a university examination. Genesis of the RMP, that means how the RMP is developed. In the last we will discuss the effect of the sodium ions and potassium ion on the resting membrane potential. So let's see one by one. So basically RMP, that is a resting membrane potential. The potential difference exists across the membrane in the resting condition. So in this image, this is the cell membrane, and in this cell membrane and across the cell membrane on the two sides there are the equal distribution of the ions. Okay, so there is a, here the difference is a 0, here the difference is a 0, so the net difference is a 0. So in this scenario, in hypothetical condition, the RMP is 0. In the second condition, in the second image, you can see here there is a plus 15 and minus 10, so plus 5. Here plus 5 and minus 10, there is a minus 5. So potential difference exists, plus 5 minus 5 is equal to 0. So again there is a RMP is a 0 in this hypothetical conditions. So now again in the three images A, B and C. Now the magnitude or strength of the RMP in this B is greater than B, A, and the less than C. Okay. So that is the strength of the RMP. So basically in the resting state there is an unequal distribution of the ions. This is the cell membrane, and across the cell membrane, for example, this is the ICF and this is the ECF. Okay. So there is an unequal distribution of the ion across the membrane. Okay, this exists at the resting state. That is called the resting membrane potential. Why this exists, that we will discuss under the heading of the genesis of the RMP. So let's see definition. So it is the electrical potential difference exists across the biological membrane under the resting state. It is called the resting membrane potential. And you must remember that RMP, the unit of the RMP is in millivolt. And always remember that the RMP is written as a minus sign. It may be minus 10, it may be minus 20, minus 30, because interior of the cell is always negative as compared to the exterior in the resting state or during the resting state. And this is the present in almost all the cells, all the living cells. So that means all the living cell having the own RMP. It may be minus 10, minus 20, minus 30, is depend on the individual cells. But yes, RMPs exist in all the living cells. But at the same time, आपको दूसरी भी fact याद रखनी है, and that is the action potential. Action potential is only exists in the excitable cell, while the resting membrane potential is always present in the all the cells. So this is the definition of the RMP. And these are the normal value examples. In the skeletal muscle is a minus 90 millivolt. In the smooth muscle it is a minus 50 millivolt. Approximate, because the RMP in the smooth muscle is always fluctuate, it is not fixed. Okay, and that is the reason it is a approximate. After that, the cardiac muscle having the minus 90 millivolt, neuron having the minus 70 millivolt, RBC minus 10, photoreceptor cell, that is a receptor present in the eyes, that is the rods and cones, they detect the light, and that's why it is called the photoreceptor. Thyroid cell having the minus 50 millivolt. Maybe there is some minor variations in the values book to book, it is also possible, but you can remember this one. These are from the standard materials. How the RMP is recorded? Recorded by the cathode ray oscilloscope, CRO. Okay, there are two electrodes. One is kept on outside ECF, one inside, that is in ICF. Okay, and the potential difference is recorded by the CRO. That is a recording of the RMP. Now coming to the genesis. तो अभी तक हमने देखा है definition, normal values and how it is recorded. Now coming to the most important aspect in this session, that is the genesis of the RMP, and this is one of the most important part of this session, that is the genesis of the RMP. So how will we main steps for the genesis of the RMP? So start with there are total 5 steps for the genesis or how the RMP is developed. Number 1, there is a selective permeability of the cell membrane, because the membrane is only selectively permeable for the few ions and not all. Okay, so maybe the few ions are the more permeable, others are the less, and some are the no permeable. Then there are the 3 equations that justify the resting membrane potential that you can write in the genesis of the RMP. So first one is a Gibbs-Donnan membrane equilibrium. Second is a Nernst equation. It is also called the Nernst potential. And third equation is about the RMP is a Goldmann-Hodgkin-Katz equations. Okay, ये क्या है और कैसे उसको explain किया जाता है, that we will discuss in the subsequent slide. In the last, we will discuss the role of the sodium potassium ATPase pump in the RMP. So first point in the genesis of the RMP, that is a selectively permeability of the cell membrane. So membrane is a freely permeable for the potassium and chloride. It is the less permeable in the resting state is sodium. ये जो भी हम बात करें, that is in the resting state, because we are talking about the RMP only, resting membrane potential. Okay. Third is the membrane is impermeable for the phosphates and protein, and you know the large number of the phosphates and proteins are present inside the cell in ICF, okay, and they are the negatively charged. Okay, so number 1 in ECF and ICF, okay, potassium, the concentration of the potassium ion is present much higher in the ICF as compared to the ECF. So based on this is the concentration gradient and this is electrical gradient. Both are in the opposite direction. They are balanced at the minus 90 millivolt, and that is called the Nernst potential of the potassium. These anions, there is a protein and phosphate are present inside the cell, that is in ICF, and they are the large molecules. So the membrane is never permeable for the phosphate and proteins, so they remain inside the ICF and they are negatively charged. So ICF is losing the positivity and at the same time it is retaining the negativity, and that's why this is one of the reasons inside the cell why become more negative. For sodium, the concentration gradient is from the ECF to ICF, and the electrical gradient is from the ICF to ECF. Both are balanced at the plus 60 millivolt, and this is the Nernst potential for the sodium. So if we look at the all together, potassium are there, protein and phosphate are also there, and the sodium are also there. So here what happen in cumulative situations, the large number of the protein and phosphate are present inside the cell. The positive ion potassium is freely moves from the ICF to ECF because in membrane is permeable for the potassium ion, and the बाहर का जो सोडियम है that is in the present in the ECF. Okay, it is not entering into the ICF because the membrane is a less permeable for the sodium in the resting state. So overall what happen, inside the cell become the more negative as compared to the outside the cell or exterior of the cell, and because of this reason the interior of the cell is always negative, and this is the example of the neurons. Okay, so in the neuron the resting membrane potential is exists around -70 millivolt. Now there are the two main factors. Number one, the ratio of the concentration of the ions outside and inside of the plasma membrane. The second one is a specific permeability. So there is ion distributions, and the second is a permeability of the membrane. These are the two main factors why RMPs exist. And this is a different in the different tissue because the individual cell having the different ionic compositions. तो ये हो गया हमारी selective permeability. Now the next are the equations which explain the genesis of the RMP. The first one is the Gibbs domain membrane equilibrium. So according to these equations, it should asymmetrical distribution of the diffusible ion across the cell membrane with cations being more inside than the outside. However, in the reality, interior of the cell is a negatively charged, which will be explained in the ensuing the discussion. So one is a Gibbs domain equilibrium, which explains the genesis of the RMP. The second one is the Nernst equation. What is the Nernst equation is also called the equilibrium potential. Which equilibrium? So balance between the chemical and electrical gradient. Okay, so जिस potential difference पे एक chemical और electrical gradient का balance हो जाएगा, at that potential difference it is called the Nernst potential of that individual ion. For example, for the potassium it is -90 millivolt. For the sodium it is +60 millivolt. For the chloride it is -70 millivolt. Calcium it is +130 millivolt. So it is different for the different ions, and that is called the Nernst potential. So Nernst potential is applicable to the individual ions, in which balance between the concentration or chemical gradient and electrical gradient. And third one is the last one equation which explains the genesis of the RMP, that is the Goldmann-Hodgkin-Katz equations. So basically, the Nernst equations is applicable on the individual ion, while the Goldmann-Katz equations is applicable to the group of the ions, and that is the main difference. And this is the equations is given here. You can see the or refer the textbook for the details. So it is the extended version of the Nernst equations, applicable to the group of the ions, as I said earlier. So magnitude of the RMP at any given point in time depends on the distribution and permeability of the variance ion. Okay, so this is very, very important for the genesis of the RMP. There is a distribution of the ions and permeability of the membrane. Now coming to the last part of the genesis of the RMP, that is the role of the sodium potassium ATPase pump. As we know, the sodium potassium ATPase pump is an example of the primary active transport mechanism. What is the main function of the sodium potassium ATPase pump? So by the sodium potassium ATPase pump, the 2 potassium moves from the ECF to ICF. At the same time, 3 sodium moves out of the cell, means from the ICF to ECF. So every time cell is losing the 3 positive ions and getting the 2 positive ions. So over a period of time, what happens? It loses the positivity. And this is also reason why inside the cell is a more negative. So basically, the sodium potassium ATPase pump playing or contributing the minor role in the genesis of the RMP. For example, कोई एक्सेल का जो भी RMP उसमें से almost 90% RMP is because of the first 4 reasons that we have explained earlier. Okay, the last 5 or 10% RMP is because of the sodium potassium ATPase pump. So in one line, if you want to explain the role of the sodium potassium ATPase pump in terms of the RMP, so it is mainly for the maintenance of the RMP rather than genesis. So this is the function of the sodium potassium ATPase pump in relation with the RMP. Now coming to the effect of the sodium and potassium ions on the RMP. So when we change the concentration of the sodium in ECA, okay, what will be the effect on the RMP? So if we change in the sodium concentration, there is hypernatremia or hyponatremia, okay, is there any effect on the RMP? No, because in the resting state, the membrane is not permeable for the sodium. So no permeability, membrane is not permeable, that means not entry, or there is no movement of the sodium from ECF to ICF or ICF to ECF, and if there is no movement of the ions, then there is no effect on the RMP. So basically there is no effect on the RMP, but yes, if we change the concentration of the potassium in ECF, then definitely affect the RMP, because in the resting state, even in the resting state, the membrane is permeable for the potassium, and because the membrane is permeable, hypokalemia or hyperkalemia can affect the RMP. So for example, if we increase the concentration of the potassium concentration in the ECF, this leads to the RMP is a decrease. That means RMP decrease matlab the inside the cell become less negative. Inside the cell become the less negative. Okay. On other side, if we decrease the concentration of the potassium, that leads to the increase in RMP. Okay. So increase potassium, that is hyperkalemia. Decrease potassium, that is hypokalemia. So hyperkalemia and hypokalemia both affect the RMP, because the membrane is permeable for the potassium in the resting state, and that's why in the resting state the potential is a difference. Potential difference is always present. So let's see one MCQ. So many MCQs from the Nernst equations, Nernst potential, from the genesis. Okay. So these are the commonest MCQ is asking in the university examination as well as in the NEET PG and next preparations. So let's see one example, one MCQ. In case of the hypokalemia, the RMP is. So in hypokalemia, RMP is a increase. Okay. So answer is a A. RMP is a increase, because of the hypokalemia, gradient is more. So inside the cell losing the more potassium, so become the more negative. So RMP is increased, matlab inside the cell become the more negative. So whenever we say RMP increase or decrease, you just ignore the minus sign, and then you have to decide whether it is increase or decrease. And whenever the RMP is decreased, matlab toward the depolarization. Whenever the RMP is increased, matlab toward the repolarization in terms of the for the excitable tissue. So answer is A. So this is all about the RMP, that is resting membrane potential. Definition देखा, there is a potential difference exists across the membrane in the resting state. That is RMP. RMP is present all the living cells, but the action potential was only present in the excitable cells. So that is the main difference between the RMP and AP. One more important part, that is the normal values that you have to remember. Method of the recordings that you have to remember. Genesis, that is the most important short note. And then in genesis there are the 5 steps. Membrane permeability, there are 3 equations, and the last is the role of the sodium potassium ATPase pump, and also you have to write down the effect of the sodium ions and potassium ion on the RMP. So this is all about the today's session. So last just look at the summary of the topic, and it is always in minus, the unit is always millivolt. There are two important factors responsible for the RMP. One is the selective permeability and the second is the concentration gradient of the ions. Most important ion responsible for the RMP is the potassium. Sometime in MCQ it is also asked, so that you remember. Role of the sodium potassium pump is more than maintenance rather than genesis. So this is all about the today's session. Thank you very much. Thank you for listening. And next video will be released on the action potential. Thank you.